Okay, good evening. I am Eric John Hubble, and I am here to talk about assignment 3, uh, specifically the task assigned to me, which is a SR implementation of a left shift register. Show the truth table or Boolean expression. Uh, so first we're gonna have to create a I'm gonna show you the SR flip-flop internals. Let's see here. Uh, so let's build an SR flip-flop with a clock. So, so here we have our finished SR flip-flop. Uh, let's put that here. So the SR flip-flop works by, we have here our S, our set block, and our R reset block or input. So if we place 1 in our set input here, if the clock runs for 1, it stores the value of S. However, you cannot reset the value even if the S is set at 0 and the clock runs. You need to uh, set a value for the reset, or set 1 for reset. So if the clock runs, then the value turns to 0. So this is useful storage. However, if both S and R are open and the clock runs, we get an error, which this LOGISIM says oscillation apparent. So we set the simulation. So there we have our SR flip-flop, and now using those principles for the SR, we should create the left shift register, but let's look first at the truth table for the SR flip-flop. So SR latching. So here we have our characteristic table. So if both S and R are 0, that means the next Q will be 0, given that the previous Q is 0. And yes, R is reset, so it's 0. At S is 1, the next value will be 1 if Q is 0, the previous is 0, and if both, it returns an error or oscillation apparent. If the previous value is 1, we can only change it if the reset value is 1. Only the reset value is 1. So that's our characteristic table, and we can see here the excitation table. So 0 from 0 to 0, S is 0 and R is any value 0 or 1. From 0 to 1, the S, you apparently need only the S at 1 and R at 0. For the previous value of 1 to turning to 0, you need the R at 1 and S at 0. And if you don't need to change 1, then any value of S and 0 value of R. So that's what we have for our SR flip-flop. Let's go back here. Now we can build a 4-bit left shift register as an example. So here we have our 4-bit SR left shift register. So as we have said earlier, if we set the value of s at 1, we can store the value of 1 in the SR flip-flop. And if we say continue to set s at 1, we reach 1, 1, 1, 1. So there's that. But if we set r to be 0, it moves the 0 in the left. Yeah, it goes from right to left. So that's how a left shift register works. It shifts to the left. So 1 on the right becomes on the left. It moves to the left. And R, as I explained earlier, if both S and R are at 1, an error occurs. So there we have it, our left SR left shift register. So our truth table for that would be, um, so here we have our uh, our truth table for the left shift register using SR. So we have our S set at 1 here. So initially it is 0, 0, 0, and if we input 1, 0 there for SR, we return this value, and so on as the clock ticks. Yes. So we have here our pattern. So when S is set at 1, uh, the Q0 here looks like that. So that's how our SR left shift register works. So thank you.